Hello, I'm Ryan Baker and this is Big Day in Education. Welcome to the third video of the third week of our class on feature engineering, one of the most important topics and least studied topics in all of Big Day in Education. Up until this point in the class, we've talked about building and validating prediction models, including behavior detectors. Models that infer a predicted variable from predictor variables. A couple lectures ago, we went into a little more detail of where the predicted variable can come from. But where do the predictor variables come from? Do they fall out of the sky? It's raining data, the data deluge. Do they come from the Office for Predictor Variables in Washington, D.C.? Man, I wish that office existed.
So in fact, they come from feature engineering, which is the art of creating predictor variables. This is a major topic in its own right. Why is it important? Feature engineering is the least well-studied part of the process of developing prediction models, but it's arguably the most important part. Your model will never be any good if your features, your predictors, aren't very good. And its importance runs straight up against the fact that right now it's an art. It's human-driven design rather than being a clear process which you can just follow from start to end with no ability. Right now it still involves lore to a large degree rather than well-known and validated principles. We need to do better. It's hard.
The big idea is how can we take the voluminous, ill-formed, and yet underspecified data that we now have in education and shape it into a reasonable set of variables in an efficient, effective, and predictive way.
Or to put it another way, we want features that are effective, but also not tautological. Some examples of tautological features might include predicting the final course grade from the grades on all the assignments and tests, which are what the final course grade is composed of. Or predicting that students who have engaged in violence will engage in violence. Now, yeah, sure, they might not always. Some students will get on the right track, some students will go off track, but in general, it's going to be pretty strongly correlated. Predicting that students who stop participating in a course are likely to drop out. By the time you've observed that they've stopped participating in the course, it might be too late to do much. That said, one person's silly tautology is another person's meaningful finding, so keep that in mind.
It's a process in its own right. You brainstorm features. You decide what features to create. You create the features. You study the impact of the features on the model goodness. Then you iterate on the features if useful, and then you go back to creating more features or brainstorming more features until you feel like you're done. Brainstorming features can be more or less formal. IDEO, which is one of the nation's leading design firms, has some tips for brainstorming. Defer judgment, encourage wild ideas. I like wild ideas. Build on the ideas of others, stay focused on the topic, have one conversation at a time, don't split into lots of groups doing lots of stuff. Be visual and go for quantity at first rather than quality. I like quantity.
When you're brainstorming features, it's good to have both educational data mining / learning analytics experts and domain experts in the room. And by domain experts, I mean people who understand the literature in the area, if there is any. People who've conducted classroom observations relevant to the construct you're interested in. People who've taught relevant to the construct you're interested in. People who have a deeper understanding of the construct, in other words, than just some random person who's never really thought about it before.
I want to point something out. Building on the ideas of others doesn't just have to be people nearby. There's a huge literature out there of features that people have tried and what's worked or failed to work for a range of problems. Read papers from researchers working on similar problems and see what you can use. On hard projects, my research group often meets as a team over pizza and beer to brainstorm. On easier projects, sometimes one person will brainstorm solo and then discuss their features with another person who will offer further suggestions. Deciding what features to create, well, there's never infinite time. You have to decide because you can't make everything. And there's a trade-off between the effort needed to create a feature and how likely it is to be useful. Sometimes the best you can do for how likely it is to be useful is look at whether similar features have been useful for similar problems and use your best intuition. It's worth biasing in favor of features that are different than anything else you've ever tried before because it explores a different part of the space.
So what toolkits should you use to create your features? Microsoft Excel. It's really good for prototyping features that you can then build in code. You can see what you're doing. It's fallen out of fashion. See past versions of this MOOC for detailed info on how to use Excel for this. Graduates from this course and our master's program here at Penn, just when they go out in the world and they use Excel for this stuff, people mock them, even though you're more likely to catch your mistakes with Excel than other stuff. But such is the world. Jupyter Notebook. Jupyter Notebook allows quick prototyping and iteration with code. It's pretty good. It's just a little bit harder to see what you're doing than Excel. Distillation code. the scalable solution, but it's harder to check yourself or explore. So there's a lot of useful types of features. Some that I've found useful in past projects include things like taking averages, minimum values, maximum values, standard deviations, taking total counts of something overall, taking counts of something so far. So this kind of aggregates up as you go and represents the past. Taking counts in the last n actions, a sliding window that doesn't look too far in the past. Differentiating the first attempt at something from subsequent attempts. Particularly important, we'll talk about this one, for example, a little more when we talk about knowledge tracing, because student performance on their first attempt on a math problem, or other kind of problems, is often indicative very differently than their performance the second or third time. The ratios between events of interest. Features based on cutoffs, thresholds. Percentages of some action type so far. Percentages of the student's time spent per different type of action, or different location in a virtual world, or different knowledge component / skill, or whatever. Another type of useful feature, did an event of interest ever occur for the student? Sometimes, if some events occurred, it really represents a difference in everything thereafter. How many times has something happened so far? Comparing earlier behaviors to later behaviors through some sort of caching. Another type of feature. So you might just look at standard deviations across actions, but you might also look at standard deviations above or below the mean. So in other words, take time. Is an action several standard deviations faster than the mean, several standard deviations slower than the mean? And you can take, for this kind of feature, means and standard deviations across students in any situation. You can take it across students in the same situation. You can take it across the same student in different situations so far. There's several options for this, in other words. And this has shown up useful in a lot of types of models. And you don't just have to stick with your initial features you build. In fact, I don't think it's optimal to just build a whole bunch of features and then build the model and never go back. Sometimes when a feature looks like it might be good, it's worth iterating on that feature, trying close variants to see if they'll do a little better. For example, let's say you have a feature, slow actions after hints, and you define slow action as an action taking over 20 seconds. Well, okay, but what if 30 seconds is a better cutoff? What if 15 seconds is? There's no guarantee that your initial choices will be the very best. Overall, the details of features matter. For example, the same feature can have a different impact depending on the context.
Take this example from Baker et al. 2015. We can take the simple feature of, has the student opened their online textbook? Seems very straightforward. But in fact, whether a student has opened their e-textbook predicts whether they fail their course, but with totally different precision and recall on the first day of class versus the 7th day of class. Same feature, just 6 days different when we look at it, but in one case, the first day of class, it catches almost everybody who won't pass the course, who will fail, but it also catches a lot of people who will pass the course. On the 7th day, it no longer captures everybody who's gonna fail, but everybody it catches is probably gonna fail just about. So, same feature, just 6 days later, totally different semantics.
Here's some tutorials for the Excel equation solver. One tip that you might find useful. For recent versions of the Excel equation solver, it actually doesn't do too good a job of searching the space compared to the earlier versions. Multi-start option is something you can use to avoid local minima that can sometimes block the solver from even getting started. I'd like to share a few more thoughts on feature engineering. First, does feature engineering overfit? Well, it can. Which is why it's useful to remember. The true test of a model is whether it works on entirely unseen data. If you iterate on your features a lot and you're using cross-validated goodness the whole time, then the cross-validated goodness will not be the true test of your model. The true test of your model will be either a held-out dataset or a newly collected dataset later on. One other thought on feature engineering. Your features come from somewhere. You can take a standard set of variables or pre-existing variables, and there's no question that's faster than engineering things. But thinking about your variables is likely to lead to better models. So in the next lecture, we're going to talk about the opposite of feature engineering, automated feature generation and selection. So I look forward to seeing you next time. I'm Ryan Baker. This is Big Day in Education. Thank you very much.